welcome to our lesson on tangent theorems. There are two theorems for tangents involving circles, and the first one is the tangent to a circle theorem. A line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So in order for this tangent right here to be tangent to the circle, it must meet a radius at its endpoint at a 90-degree angle. So we often see this used with right triangles. In our first example, we are asked, is EF tangent to circle G? So if it is tangent, then right here we would have a 90-degree angle. And what we did was we set up endpoints on the tangent, and then this segment was set up from that point to the center of the circle. And so this ends up being the hypotenuse of a right triangle. And we can test if this would make a right triangle by using Pythagorean theorem. And if we have a right triangle, then we know we have a right angle. So then go ahead and do the math. 9 squared is 81, 40 squared is 1,600, and 41 squared is 1,681. So if I add these together, then the numbers agree on both sides of my equal sign. So then we know that yes, EF is tangent to circle G. Example 2 asks, is IJ tangent to circle H? So just like our last example, we can take the values that were shown and plug them into a squared plus b squared equals c squared to see if that works out. The only difference here is that where we have your radius right here, remember that would be equal to a radius over here because they did not give you the full line segment. They only went from this point to J and made that 8. So the part that's missing right here is 5, and we have to combine these to get the full length of the hypotenuse. Let's pause the video now and determine, is that a right triangle? So yes, everything works out. We do have a right triangle here, so we do know that IJ is tangent to circle H. Remember, if you have your Pythagorean triples memorized, like 5, 12, 13, you could actually skip the step of using Pythagorean theorem, and you would be able to just say yes. Number 3, LM is tangent to circle K, solve for X. So in this one, we already know that we have a right angle right here. So we have a right triangle, so pause the video to solve for X. Again, in number 3, if you have your Pythagorean triples memorized, 7, 24, 25 is a very common one. So you could have skipped the work, but if you did show the work, you should have still gotten that X equals 24. Our second theorem involves two tangents. Tangent segments from a common external point are congruent. So if I have my tangents originating from this point here at P, from P to N, and from P to O are congruent to each other. So this actually ends up looking like a comet. You have the circle, and then the two tangents that connect, it looks like a little comet tail. So remember that the two parts of your comet tail are equal to each other. So in example 4, when we want to solve for X, we simply need to take the two parts and set them equal to each other. And it's as simple as that. In example 5, we want the length of xy, so after we solve for x, don't forget to plug in. Pause the video now to solve number 5. If for number 5 you got that xy equals 21, you are correct. Another way that you might see this theorem pop up is when you take a set of common tangents, like let's say BD and BE, and then combine them with other tangents like AD with AF, and CE with CF. So now it looks like you have a triangle, and it might look a little bit confusing, and the question is asking you to find the perimeter of triangle ABC, but it's still using your congruent tangents that are coming from a common point. So when we are given that BE equals 5, we know that BD also equals 5, which means AD would equal 15, just like AF, and CE equals 12, just like CF. So now, in order to find the perimeter, all we have to do is add all the numbers. And so our perimeter is 64. This concludes our lesson on tangent theorems.